bom, pessoal, nós vamos hoje apresentar um experimento relacionado a impacto em tubos, e para isso eu estou tendo a assistência do meu aluno de doutorado Henrique Ramos, do nosso técnico Eric Reis, e nós vamos então começar a descrever o experimento e vamos trocar agora para a língua inglesa. Okay, so we are starting now an experiment where we are going to demonstrate the collapse of tubes, and I have the assistance of my PhD student Henrique Ramos and our technician Eric Reis. Okay, so I have to take the mask because of the quality of the sound, and this experiment is taught in a course at the University of São Paulo, Department of Mechatronics, called Instrumentation, which is taught together with my colleagues Dr. Larissa Diremeyer and Dr. Rafael Traudi Moura. What we have here, it's a very in a way redundant system of experiments, of sensors, because we wanted to draw your attention to the various features that we can get with different sensors in order to monitor the behavior of our specimen, which is the one we are going to be focused on. Okay, so surrounding this experiment there will be quite a few equipments, and I'm going to describe all of them, so this will take a bit longer, and at the same time I'm going to give some motivation for why we are studying the collapse of tubes, which in the end is what we wanted to study. So I have here a tube, and later I'm going to take some measurements of this tube. This tube is made of aluminum, and what we wanted at the end of the day is to get this mass, which at the moment is 14.2 kilos, and get this mass and raise it, and then because we raise it has potential energy, and when we release it's going to transform this potential energy in kinetic energy, and which needs to be supposedly absorbed. And this is going to be absorbed by the collapse of this tube. And the idea behind is that if I can absorb kinetic energy, I can dissipate this energy, and in connection with crash of cars, then I can profit from this phenomenon because I can, by dissipating the kinetic energy of my car when colliding against a wall or another car, I can get less energy to my body and so less damage. So then the collapse of tubes and similar structures are quite well connected with the crash systems that we find in cars nowadays, and then there are different names for these systems that are used in the cars, like deformable programmed structure, for instance. Okay. So then I'm going now to present the systems, the equipments that we are going to use, and then we carry on with the demonstration. So one big motivation of our group in studying the collapse of tubes is related, as I said, to the dissipation of kinetic energy. So in a way, we can call it dissipators of energy. And why we have this interest? Because particularly in our location here in Brazil, the number of accidents, car crashes, victims and fatalities and so on is quite large. So we are talking about somewhere around 40,000 people dying each year in car crashes in Brazil. And perhaps half of these, or a bit less, or half, is related to motorcycles car crashes, motorcycle accidents. So then this gives a background for us to give importance to this phenomenon, for us to then study it and then apply for the better of the society. So then Brazil has quite a few restrictions on the security of the cars, but even though our standards, the cars that we are producing, are not yet the same standards as we find in European countries or American country. So then we need to give some importance to these regulations and make them tougher so we can get safer cars, and then in a way this is what we direct our efforts to in order to meet this demand of the society. So the collapse of tubes, we could call also shells or cylinders or and so on, it's quite well studied in the impact engineering field because of the reasons I told you in terms of improving the absorption of kinetic energy. Okay, the phenomenon is quite complex because we have wave propagations, elastic wave propagation. When we hit a tube, we have plastic wave propagation, we have global and local modes of deformation, we have strain rate, material strain rate sensitivity, and we also have a phenomenon that has been discovered recently of inertia sensitivity. Recently, I mean in the last 10 years. Here I'm going to show you a tube that initially was a straight tube, circular, okay, and then I applied enough energy to go for promoting the formation of these wrinkles that we call, we call it a wrinkle in English. And then I can hardly say whether it started the impact on the top or if it started on this way, but I know because it's marked inside here that it started this way. So then it's going to form one buckling shape first, followed by the second, followed by the third and fourth, and so on. So it's going to be a sequence of the formation of these wrinkles, and then that's why we give the name for this phenomenon as progressive buckling of shells or of tubes. Okay, and the same we are expecting to get today when we do this demonstration for you. We can also do, of course, in squares like this, cross-section, square cross-section tubes, where we have also this progressive mode, and we can do in longer tubes, and in longer tubes you can get this. We get lots of progressive buckling shapes one by one, but eventually the speed of my indentation, of my impact mass, is going to decrease because the kinetic energy is being dissipated, and then eventually because the velocity decreases, the tube tends to go to another buckling mode. This buckling mode is the more traditional one called Euler buckling. So it's the buckling of a column, like eventually, if you can imagine this was on the top here, it buckled like this, eventually fell out of the support and so on. Of course, this Euler buckling is not efficient for dissipation of kinetic energy, this one, progressive one, being more efficient. So we have progressive buckling, we have Euler buckling, or the buckling of a column, and we have also dynamic buckling. Dynamic buckling is characterized by small wrinkles that we hardly can see, but we can see, but the wrinkles are smaller, and they happen due to a high impact velocity of my mass, so around above 100 meters per second, more or less. The velocities here are around 10 meters per second, 5 meters per second, and even statically we can get similar shapes like this. This is a cross section that we cut for you to see how it is, and you can have very different shapes and very interesting shapes as well, okay, which are not symmetrical in this case, much more difficult to be tamed by a theoretical framework, so then this is more difficult. And on the other hand, there are quite a few models that explain well what happens with this tube, and then later we can apply this sort of knowledge to estimate the dissipation of energy and also the medium load and so on. Okay, so what we want is to test this small tube, okay, by dropping a mass on the top. For that, we are going to use this, we call a mini tower or an impact hammer or a free fall tower. There are different names. So this was designed here by our team. It has a large inertia for this sort of mass and this sort of tube. The base here is quite large, is 1 ton more or less. We are dropping a mass of 14.2 kilos that I'm showing here. Okay, there are another tube here. I can put my hands underneath because I'm holding my system by a magnetic device, okay, and hung on this in all this system here we have the light sources, because we wanted to illuminate the scene quite well. We have special LED bulbs here that I'm going to show you later how we use it. And also we have on the top there a laser, and this laser is going to be used. You see on my hand here the signal of laser, okay? So then it's going to be used for the measurement of the velocity of this falling mass along the whole trajectory, since the beginning when the velocity is 0 until the end when the velocity is 0 again. Okay, so but we have an acceleration because we are under the gravity field, and then this is a free fall. The velocity is going increase, but when it hits the tube here, the velocity is going to decrease, but it doesn't go to 0 immediately. So it's going to decrease. There will be a variation of the velocity, which will give acceleration, and then the acceleration, the acceleration times this mass is going to give the force. Okay. Well, as I said at some stage, the experiment is in a way redundant, because force could be measured by this laser system, okay, but could be measured by a load cell that we put on the bottom here, okay. This load cell is there on purpose for us to add another sensor, and then to explain this sensor for you and explore it as well on the experiment. In terms of principle of these devices, let's talk a little bit about the laser. The laser is such that there is a laser beam which has some frequency coming out from my tube there, okay, my canyon, and then the laser beam hits a reflective tape which is connected to this mass, and this reflective tape has the property, of course, to reflect back the laser to a head measurement that is inside the system there. So then I have a frequency coming out and a frequency coming in. But due to Doppler effect, there will be a change in the frequency coming in to the laser because the reflective tape is moving the speed according to the speed of the mass. Of course, it's connected. So then this difference in frequency can be related. There is a simple equation, is the difference in frequency times the wavelength. No? You can make a connection with the velocity of the mass or of the source of this variation of frequency. So then this basically is the principle of the laser, and of course the signal goes to a setting that I can set the relation between voltage, which in the end of the day is what the system is, outputs, voltage related to the velocity. So in this case here, at the moment, I'm having 2 meters per second being 1 volt. Okay, so and then I can, how can I calculate the acceleration? Well, the acceleration is going to come from the derivative of this velocity signal. Well, as I told you, we have also a load cell that is on the bottom here. Okay, the load cell then will measure directly in newtons the force. Okay, it's a washer made of a piezoelectric material, and the signal outputs straight to a preconditioner. The load cell we are using is Kistler. The preconditioner is here. Essentially transforms the charge, which is given usually in picocoulombs, in newtons straight away. So then this is a charge amplifier, which gives as an output of the charge amplifier the voltage. Okay, and the voltage is collected by a system that I'm going to describe later. So these washers are made of a piezoelectric material, which has a property when compressed they release these coulombs, these picocoulombs, and then we can make a relation with the load. So then on one hand we have a velocity system, which we are going to apply a derivative of the signal to get the acceleration and multiply the mass by the mass to get the force, and on the bottom we have the load being measured directly. Okay, so if we go now a bit more to the instrumentation side, we are going to talk about the amplifiers and the communication board. Okay, so now we are going to talk a little bit about the boards, because all the signal from the laser we saw before and from the load cell, they are collected by this board. This is a board from the National Instrument, okay? And then we can get the inputs on this train of pins here, okay? The inputs of my signals, or you can also input analog signal with the BNC as shown here, and then we can output them straight with a USB cable and connector. We can output straight to my computer here. So this computer in the end is the one which is going to collect all the signals. There is a sample on the screen now for you to see. And then we had to write a little code on LabVIEW, we could also collect it with reading the channels in MATLAB, for instance, but we are using LabVIEW here to get the signals from the load cell and from the laser. We could also get a third signal from our system, which is, I'm going to show you not in many details, but there is a magnetic tape in the back here, okay? And this magnetic tape, closer to it but connected to the mass, there is a head which senses the change in the magnetic field via the Hall effect, because this tape here has north and south poles recorded along the length, and then as the sensor, this head, moves together with the mass along the tape, it keeps counting how many changes, switches of north and south pole occurred, and this is in the range of microns. So then I can have the position of my mass along the whole train of distance here, and then I can use it to switch on and off the motor that is on the top of my drop hammer there, to position the mass in where I want it. So if I wanted 1 meter, I can move it 1 meter high or so. We are not going to do this, to use this automatic system on this experiment today, and we are going just to set the height with a normal rule for us to apply the energy. The other thing that I would like to highlight to you is this camera. Okay, this camera has the capability to film at a high rate of frames per second in this case. Okay, so we can set this camera recording at 100 frames in 1 second. Okay, but we can set also to 100,000 frames in 1 second. So the range is huge here. This is related to the memory and so on. There are other issues behind. But for this experiment, typically we can run and see very well what happens frame by frame if we set something between 1,000 and 10,000 frames per second. So then later we are going to use a software where we are going to put all these settings for you to get acquainted with. And of course, when I see the image, for me to film well with a good quality, I need quite a lot of light in the system. So then I have these 2 sets of bulbs, this one and this one, that I can change a little bit the position here for you to see. Okay, and all this can be seen there on the video. You see in the video there, I can put the tube here to show you that is live, and then we can see now in the camera what we are going to film. And so now, because it's in a live mode and without filming, I don't need special lights, but when we are going to film, we do need these special lights. So the mass value is 14.2 kilos. Okay, it's important that when we do impact tests like this, the masses are very well connected, and this might not be right the case here, because we wanted to have flexibility in the assembling of different masses for different tests, but for our purpose here it should be okay. So then we set already the mass on the position. This position at the moment is 85 centimeters, and then we are going to start the test, which is going to be a command for us to release the mass, and once the mass is released, it's going to fall. When it hits the tube, is going to give a peak both in the load cell and on the laser system, and we are going to use the signal of the laser to trigger the system, which means start recording load cell and laser system, and Henrique is going to manually to start the camera once the mass is halfway through, and then the camera is going also to record the, the phenomenon. The images we are going to collect, the film, is for us to see what happens, but we are not going to take qualitative measures of the image, although this would be possible with special softwares. So then Eric is setting for the LabVIEW to be ready to collect the data. The lights are now on. They are set on not automatically but manually. The release is going to be by the button, the red button there. Okay, and they two, Henrique and Eric, are going to communicate with each other for them to get the test done. So the tube has been collapsed, and then we are going to show you now what we measured. So the result of the test is this tube. Okay, I collected from the platform. You can see that, of course, decreased the length and formed two wrinkles here, and these wrinkles have a theoretical expression that later we can check. And so for us to check against the experiments I'm going to measure, so then this is 4.3 millimeters. Okay, and as you can see, the first wrinkle here is well defined. The second was needed a little bit more of energy to be formed, to be completed. Okay, so we are talking about energy for one wrinkle, one hinge and a half, but we have a little bit of plastic dissipation on the top, so then we can roughly indicate that we had two wrinkles in this experiment. And then you are now seeing the video, and then you can see the formation of the wrinkles for you to make an assessment of what happened. And later we are going to do the numerical simulation. This is a topic of another set of films, the numerical simulation in Abaqus of this phenomenon. And then you are going to see that it's required for the Abaqus to run the material properties. And then I anticipated that it's difficult to get material properties from the tube because of the shape it has. So then we are going to get around with this by doing a transverse compression of this tube. And then I'm going to explain in another video what is the purpose of that and how we are going to get, by interpolation and so on, the material properties. So, well, for us to be acquainted with the phenomenon in terms of hands-on, we recorded the data for you from the load cell signal a long time, the laser signal or velocity a long time, and with these two information you could be curious enough to compare whether the load signal matches well or not with the laser signal. So then you have to apply the derivative and so on, as I explained it to you. And there is a worksheet that gives information step by step how you can get do this procedure. This data we are going to upload also on the system, so then you can access it for you to do the manipulation required. Well, thank you very much for your attention, and I hope you enjoyed the video today.